Hello everyone. In previous session, we have discussed Lagrange's theorem and two results using Lagrange's theorem. Now, in this session, we will discuss consequences of Lagrange's theorem. The first one is Euler's theorem. The statement of the Euler's theorem is, if n is a positive integer and a is relatively prime to n, then a to the power phi of n congruent to 1 modulo n. Let us prove this theorem. The proof is as follows. We know that the set Gn of all positive integers less than n and prime to n is an abelian group under multiplication modulo n. But positive integers less than n and prime to n is denoted by phi of n. Therefore, we have the order of Gn is phi of n. Let A is equal to Qn plus R, where Q is a quotient and R is a remainder, and these two elements belongs to Z, with the remainder R greater than or equal to 0 and less than n. By data, the GCD of A and n is equal to 1, which implies we have the GCD of R and n is also equal to 1, which implies we have R belongs to Gn because R is relatively prime to n and R less than n, therefore R belongs to Gn. We know that if G is a finite group of order n, then we have a power n is equal to e for all a belongs to G. Now, Gn is a finite group of order phi of n and R is an element of Gn. Therefore, we have R to the power phi of n is equal to identity of Gn. But the identity of the finite group Gn is 1. Therefore, R to the power phi of n is equal to 1. Now consider A is equal to Qn plus R, which implies we have A is congruent to R modulo n, raising the power phi of n on both the sides. We have A to the power phi of n congruent to R to the power phi of n modulo n. Here, R to the power phi of n is equal to 1. Therefore, A to the power phi of n congruent to R to the power of phi of n modulo n becomes A to the power phi of n congruent to 1 modulo n. Hence the theorem. The next consequence is Fermat's theorem. The statement of the Fermat's theorem is, if p is a prime number and a is any integer, then a power p congruent to a modulo n. The proof of the Fermat's theorem is as follows. Let us prove this theorem by two cases. Case 1. Let the GCD of A and P is equal to 1. That is, A and P are relatively prime. Then, by Euler's theorem, we have a to the power phi of p is congruent to 1 modulo p. But we know that phi of p is equal to p minus 1, where p is prime. Therefore, a to the power phi of p is congruent to 1 modulo p becomes a to the power p minus 1 congruent to 1 modulo p. Multiplying a on both the sides, we have a into a to the power p minus 1 congruent to a into 1 modulo p. On simplification, we have a to the power p congruent to a modulo p. Let us see case 2. Let the GCD of a and p is not equal to 1. That is, a and p are not relatively prime. Now, the GCD of a and p is not equal to 1 and p is a prime, which implies we have p divides a. Therefore, we have a congruent to 0 modulo p. Raising the power p on both the sides, we have a to the power p congruent to 0 to the power p modulo p. But 0 to the power p is equal to 0. Therefore, we have a to the power p is congruent to 0 mod p. We know that if p divides a, then p is also divides minus a. Therefore, we have 0 is congruent to a modulo p. We know that if a congruent to b modulo n and b congruent to c modulo n, then a is congruent to c modulo n. Similarly, we have if a to the power p is congruent to 0 modulo p and 0 congruent to a modulo p, then we have a power p is congruent to a modulo p. Hence the theorem. The next consequence is every finite group of prime order is cyclic and hence abelian. The proof is let G be a finite group of order P, where P is prime, that is, order of the group G is equal to P. Let A not equal to E belongs to G and H is a cyclic subgroup of a group G generated by an element A. Since G is a finite group and H is a subgroup of G, then we have by Lagrange's theorem order of H divides order of G. But order of G is equal to P, therefore we have order of H divides P. Since P is prime and P has no divisors other than P and 1. Therefore, we have order of H is equal to P or order of H is equal to 1. But we can't take order of H is equal to 1 because if we take order of H is equal to 1, we have A is equal to E, which is contradiction to the fact that A not equal to E. Therefore, we must have order of H is equal to P. Since P is equal to order of G and H is subset of G, therefore we have G is equal to H. But H is a cyclic subgroup generated by an element A. Therefore, H itself is a cyclic group, but H is equal to G. Therefore, G is also a cyclic group. But we know that every cyclic group is an abelian group. Therefore, we have G is cyclic and hence G is an abelian group. Hence the theorem. The next one is, if G is a cyclic group of prime order, then G has no proper subgroup. Let us prove this consequence. Let order of G is equal to P, where P is prime. Let H be any subgroup of G. Since G is a finite group and H be a subgroup of G, then by Lagrange's theorem we have order of H divides order of G. But order of G is P, therefore we have order of H divides P. Since P is a prime number and P has no divisors other than P and 1. Therefore, we have either order of H is equal to 1 or order of H is equal to P. If we take order of H is equal to 1, then we have H is equal to the singleton set containing an identity element E. Or if we take order of H is equal to P, then we have order of H is equal to order of G, and H is a subset of G. Therefore, we have H is equal to G. This shows that G has no proper subgroup. Thank you.